All right, guys, we're going to be talking about graphing tangent and cotangent in these notes. Let's go ahead and get started here with a quick little warm-up. These are some equations we're going to need to be able to solve in order to find the asymptotes on these graphs. So go ahead and take a moment and pause and try to solve these. Okay, I'm going to go ahead and do them here. Again, if you want to do them before and kind of check your answers, make sure just to pause the video and try them. Okay, so let's go ahead and solve this. We're solving for x. We need to add pi over 4 to both sides here. So add pi over 4. In this case, we are adding fractions. We're adding half of pi plus 1/4 of pi. We can sort of think about it 1/2 plus 1/4. We probably already know what this is, right? 1/2 is the same thing as 2/4. So 2/4 plus 1/4 is 3/4, right? So we're going to get, on this side, we're going to get 3/4 of pi, or 3 pi over 4, equals 1/2 x. And then to solve this, we could divide both sides by a half, or we could multiply by 2. However, you want to get rid of this fraction here. I think it's a little easier to multiply by 2. So multiplication by 2 cancels that out. We get x equals, well, we have to multiply this by 2 also. A little bit of simplifying here. These are both divisible by 2. So we end up with, right, the 1 kind of cancels that one out there, 3 pi over 2. So in this case, if this was an equation we needed to solve for an asymptote, this would be the equation of one of our vertical asymptotes. So along the x-axis at 3 pi over 2, so pi over 2, pi, 3 pi over 2, we'd have a vertical asymptote right there. We'd draw one like this, right? Vertical asymptote. Again, we'll talk way more about the vertical asymptotes. I just wanted to say like how I'm actually taking this information to apply it to what we're going to be doing next. All right, let's go ahead and move forward and solve this next one. Very similar equation, right? The only difference here is that there's a negative in front of the pi over 2. Otherwise, it's exactly the same. So we're going to be adding pi over 4 again to both sides. That's going to give us 1/2 x equals, now we have a little bit of something different. This is a negative, so it's negative 1/2 plus 1/4. Negative 1/2 is the same thing as negative 2 over 4. Adding those together, we actually get negative 1/4, or negative 1/4 pi, or negative pi over 4. And then to finish this off here, would you need to multiply both sides by 2 or divide by half? I think the multiplication is a little bit easier. And we get for this one, x equals negative pi over 2. Again, same idea here. These cancel. We're going to get a 2 in the denominator. So negative pi over 2, we would have another asymptote over here at negative pi over 2. We can kind of sketch that in. And for tangent, our graph would exist in between here. Again, we haven't really learned about that officially yet, so we'll talk about it later. But these would be our asymptotes, and yeah, we'll solve equations pretty similar to this. All right, let's go ahead and move forward and work on these things. So here are the basic versions of these graphs. So I'm going to try to emphasize a few things about them. The one on the left here is tangent, and one on the right is cotangent. Some important things just to sort of notice about them. In general, tangent is increasing. It starts down low on the left and it increases up and to the right. Obviously, if we put a negative in front of that, everything flips and it actually is reflected. So then it would be decreasing version of this. So that can change, but in general, tangent is increasing by sort of default, so to speak. And then cotangent is going to be decreasing by default, right? It starts up high on the left here and then decreases. Another thing to notice is kind of the general placement of the graph, sort of where they start. You'll see how tangent exists in between these numbers, negative pi over 2 and pi over 2. Those are where the asymptotes are. This is just one cycle for each of these. I didn't mention that before. This is just one cycle. It keeps repeating itself over and over and over again. We can check those out on Desmos here in a little bit, but this is just one cycle. Tangent exists between negative pi over 2 and pi over 2. And cotangent exists between 0 and pi. Yeah, so just kind of where the graphs are placed are kind of different. You'll also notice that the cycle of these, if these are indeed one cycle, are a little bit shorter than we're used to seeing, right? This distance here between negative pi over 2 and pi over 2 is only a distance of pi. So it tells us that our period here is actually just pi. That's different than the other ones, than sine, cosine, secant, and cosecant. Those all had a period of 2 pi. So this period is actually half of that. And that's the same here as well. We're going from 0 to pi, so a period of pi. We'll get into more stuff that's going on here in a little bit. I just wanted to mention some real basic things and just kind of demonstrate our basic shape. All right, let's go ahead and move forward. So the quotient identities. The quotient identities are going to help us sort of identify where the asymptotes are. So hopefully you remember that tangent can be written as the quotient of sine over cosine. And cotangent can be written as the quotient of cosine over sine. What that does is that actually causes there to be some undefined values, right? Anything that makes cosine equal to 0 would cause tangent to be undefined. And we know on our unit circle, there are a few different places around the unit circle that cosine is undefined. That cosine is 0. So there's cosine 0 here at pi over 2. And if we rotate in the negative direction, right down over here, it says 3 pi over 2 on our unit circle, but I could also think about this as negative pi over 2 if I'm thinking about this as a negative rotation. Those angles would be coterminal. But anyway, cosine is 0 there, which again makes this undefined. So there's two places, pi over 2, negative pi over 2, where cosine is 0, thus tangent is undefined. If we actually go back to that previous slide, negative pi over 2 and pi over 2 are actually the locations of the asymptotes. So where it's undefined, there are asymptotes. We'll talk about why here in a second, but that's kind of an interesting concept that's going on. And then if we examine cotangent as well, again, cotangent is going to be undefined anywhere sine is 0. And there are a couple of places, right? Sine is 0 here at 0 radians, and sine is 0 here at pi. 0 and pi, 0 and pi, those were the places where we had asymptotes for cotangent, right? 0, pi, asymptotes. Cool. So wherever it's undefined, that's where we're going to have the asymptotes. Well, why is it asymptotes? We learned last semester there's a lot of different ways that we could have something be undefined. We could have a hole. We could have kind of a jump, discontinuity. We could have all kinds of things. Asymptote is just one of those. Well, that's because we're dealing with a ratio in this case. So when we think about this, as cosine gets closer and closer and closer to 0, it's approaching 0. What's happening with this ratio? Well, let's just kind of examine a place where that's happening, right? Cosine is approaching 0 here, but sine is approaching 1. So we're approaching something that's like 1 over some number that's really, really, really small. It's getting closer to 0, so it's getting really, really, really close to a small number. The smaller this number is, the bigger this becomes. So this is actually growing without bound. And the closer we get to 0, the bigger this number is. So we are actually having that situation where it's going, and then the closer we get to 0, it's just going up vertically to infinity, which gives us that asymptote behavior, right? It's going, the closer we get to 0, in this case, this being 0, the more that fraction, that ratio there is actually growing without a bound towards infinity, essentially. Same thing is happening with cotangent at these other places at 0 and pi, but just it's all about this concept of we're getting essentially 1 over a very, very, very small number. The smaller that number is, the larger the output we get, thus growing without a bound. That's that vertical asymptote behavior. All right. So here are the basic steps that we're going to follow while we're graphing these. We'll go through them in more detail, but They're a little bit different than what we learned for like sine and cosine and tangent, or secant and cosecant. So the first thing we're going to do is we're going to find the asymptotes. This is really only for one period. Obviously, it's going to keep repeating infinitely, just like all these other graphs in both directions. But this is just for one period. We're going to find the asymptotes. The left side asymptote, the right side asymptote, and there. And the way that we do that is we take what's inside of our tangent or inside of our cotangent and set them equal to those values that make them undefined. So for tangent, we set that equal to positive pi over 2 and negative pi over 2, because those are the two places that tangent is undefined. And then for cotangent, we set those equal to 0 and pi, because those are the places that cotangent is undefined. That's just something we have to remember. We have to remember with cotangent, we use 0 and pi, and with tangent, we use positive and negative pi over 2. After we do that, we can kind of set up the scaling along the x-axis. That step's not really in here, but kind of a step right here. We have to scale the x-axis and draw the asymptotes and everything. So we kind of scale the x-axis so we can put these asymptotes on there, and then we draw them in place. And then we make sure that we've divided that space up between our asymptotes into 4 equal parts, 1/4 increments. So what I'm saying by that is we have our asymptotes, right? Just like all of these graphs, we need 4 even increments here. So whatever our scaling is that needs to make that happen, we have to find the middle of the asymptotes, we have to find the 1/4, and we have to find the 3/4, because we're going to use those places to actually plot points. And that's the next step. We actually plot the 3 points for either tangent or cotangent. Now, both graphs kind of work similarly in this case. I'll focus on what tangent sort of looks like. In the middle, it's on its midline, so we'll just assume this is our midline. At the 1/4, this distance here is our amplitude. The distance from the midline to this point is our amplitude. And then the same thing that's going on here, this distance from here to here is the amplitude, whatever that happens to be. Just like in all of our other functions, if it's a 2, that's 2 units. If it's a 5, that's 5 units. If it's a half, it's a half a unit. And then I know this one is a tangent because we're generally going uphill. We're increasing here. We're starting low on the left and going up on the right. If it was a cotangent, I would just kind of reflect these and graph it in that manner. But after that, once we have these 3 points graphed, then we sort of just plot the curve as best we can, making sure we approach the asymptotes and ideally pass through all the points. So that's what we're talking about here in sketch the curve. I did miss some things here kind of in this stage where we're graphing the 3 points. We do need to make sure that the y-axis is scaled appropriately here, because we need to make sure to graph the amplitude and the midline and all that stuff in its proper location. So it's a little bit different of a process than sine and cosine or secant and cosecant that we've learned so far. Honestly, sometimes it's easier because there's less fiddliness, especially along the x-axis, than some of these other functions. All right, let me go ahead and clear this here, and we'll move forward. I'll keep making note of that and everything, but let's move forward. So here's a kind of a sketch of those 3 points. So this is a lot like our 5 friends method, but we have kind of a 3 points method for this. Wherever the midline is, right, it's drawn in here. It might be the x-axis if there's no vertical shift, or if there's a vertical shift, wherever that is, that's where we get that midline. Right, that's the plus or minus d that goes on the end of our equation. That's where we're going to place this. I like to kind of make my graphs starting in the center here. So I graph this center point on the midline, which one-ever it is. Again, that's in the middle of our cycle, exactly in the middle of our cycle on the midline. Both of these graphs are done exactly the same way from there. Then I think about my amplitude. How high or how low above that midline do I need to go? And so then at the 1/4 point and at the 3/4 point, I need to make those other places. So for tangent, It's kind of got this general upward slope to it, so to speak. Right? It's increasing, and cotangent, it's kind of decreasing. And so we just need to measure out this distance here based on whatever the amplitude, the A value is for our equation. And then cotangent generally kind of decreasing, has that kind of negative slope to it. And once we have those points, we just kind of sketch it in, sketch that curve as best we can. We don't need to be extremely precise here. It's not about extreme precision. If we want a really accurate graph, we'll just use Desmos or something, right? The only thing to keep in mind that can switch things up is, just like all of our other functions, we can have a reflection. So we could have like y equals negative cotangent of x. What that does is reflects everything over the midline. So this point would reflect down here, and then this point would reflect up here. And our negative cotangent graph, well, it would kind of look like a tangent graph, right? It's going to have that uphill slope, that increasing relationship instead of the decreasing relationship. So you do still got to pay attention to whether there's a reflection, because that does change things a little bit. I'll keep referencing this idea of these 3 points and how the amplitude and midline all work together while we're graphing these today. All right, so let's jump in to an example. So here's our equation. It doesn't look super complicated, but there is a fair amount going on. I didn't start with a super easy one. Yeah, let's go for it. So here we have our inside of the tangent. So this is everything that's inside the tangent function. It's our b times x minus c part. It's all in there. We use that again to find our asymptotes. So for tangent, we have to set this equal to positive and negative pi over 2. That's how we find our asymptotes. So we'll go ahead and do that. And that's step 1. So I will do that. We have 2 times x plus pi over 2. And we'll set that equal to pi over 2 first. All right, so we need to get rid of this 2. So we could divide both sides by 2. We could multiply both sides by 1/2. We could even, frankly, distribute. It's totally up to us in terms of what we want to do with this. I'm just going to divide both sides by 2 to get rid of it. But yeah, you have options here. X plus pi over 2 equals pi over 4. All right, half of a half is a fourth, so pi over 4. And then we need to subtract pi over 2 to get rid of this, minus pi over 2. So now we're in the situation where we're doing 1/4 minus a half. 1/4 minus a half. That's going to give us negative 1/4. Remember, half is 2 over 4. Hopefully you can kind of get these without doing too much extra work here on the side, but I'm trying to explain my thinking here. So we get x equals negative pi over 4. So that's going to be one of my vertical asymptotes. Let's go ahead and put that on the graph. I did already scale this one just to try to keep it a little bit easier, but here's my place, negative pi over 4. I did run out of space here a little bit, so let's try this again. Let's erase some of this stuff and just go for it again. So we set it equal to negative pi over 2. Now let's set this equal to, or sorry, we set this equal to pi over 2. Let's set this equal to negative pi over 2 to get our second asymptote. Hard to keep that in mind, what I'd already done, but found one asymptote. Let's now find the other. All right, similar idea here. Almost the same equation, right? The only thing that changes is negative. So we can go about it the same way. Again, if you want to distribute and work from there, you could do that. If you want to divide by 2 like we did last time, we have options, but I'm just going to go the same way. Should be easy. That's going to give us x plus pi over 2 on the left-hand side, and then negative pi over 4. Okay, and then we just need to subtract pi over 2. Subtract pi over 2. That's going to give us x equals, so this is negative 1/4 minus 1/2. That's going to be negative 3/4. So negative 3 pi over 4. Negative 3/4 of pi. Okay, we have all this graph on the right-hand side, but we don't seem to need it, but it is what it is. We'll just put our vertical asymptote right there. All right, so here are our 2 asymptotes that we're going to use to graph this. pretty narrow looking graph. It's mostly set up for us. Yeah, mostly set up. It's going to be fine. We already have it split into 2 parts. We do need to split this into 4 parts. Since this is so narrow and I don't really have a lot of space, I'm not even going to do anything other than just mark these. If this was spread out a little more, I might write the scaling in here, but it would be very, very cramped. I'm just going to leave it as is. I'm just going to put some marks in there so that it's now in 1, 2, 3, 4 increments. In fact, I'm going to even that out a little bit better, just so that it looks good. Okay, so 4 even increments, 1, 2, 3, 4. So we've got that done. And the scaling is already done for us. At this point, we would have had to kind of do this scaling, but since we already have a nice graph here, we don't need to do that. The next thing is to start graphing these points and talk about the y-axis and the amplitude and the midline and all that. So in this problem, our amplitude is 3. We're going to be going 3 above the midline and 3 below the midline to plot some points. And speaking of the midline, it's actually 0. We technically have a +0 here on the end. There's no vertical shift, so midline is going to be on the x-axis this time. Well, so here we go. We can start graphing points. I start these graphs in the center, so in the middle of our cycle, on the midline. And again, the midline here is our x-axis. It's 0. And it's a tangent curve, so we're going to be generally going uphill with it, right? We're going to be doing something like that's going to be increasing. There's no reflection to it, so it's going to be a regular tangent shape. At this 1/4 mark, we now need to go down the amplitude. So we need to go down 3 units. So 1, 2, 3. We're going to be all the way down here at -3, the 1/4. And then at the 3/4, we need to go up. We need to go up the amplitude. 1, 2, 3, right here. This is why we call it sort of a vertical stretch, because it's not technically an amplitude, but I'm just using amplitude because that's some common language we have from some of the previous graphing techniques that we've had. So those are the 3 points we need, right? We just kind of plotted these 3. It's a little more stretched out vertically than we're used to, or scrunched in horizontally, however you want to think about it. Now it's just a matter of trying to draw in a nice smooth curve. So I'm going to try to do this neatly. Always find this a little bit difficult on the computer. So we go through here. And we're going to keep going there, and then we curve down along the asymptote. Same here. We're going to go here, and then we're going to curve up along the asymptote. Again, this one's been sort of scrunched down so that the curve is not as accentuated here. It's been squished in or stretched out vertically, however you want to think about it. But that should be a somewhat accurate tangent graph. Oops. Keep trying to erase things. All right, so yeah, there's our first example. I'm going to do one more here and then split this into 2 parts. So here's one for you guys to try. Again, feel free to pause it and kind of try this one if you want. I'm going to go ahead and get started on it myself. So again, remember, find the asymptotes first. So take what is inside your tangent. And for tangent, you set that equal to positive and negative pi over 2. Okay, well, 1/2 x equals negative pi over 2, and 1/2 x equals positive pi over 2. I should have enough space here to solve both of these, and they're pretty easy equations. We just need to get rid of this 1/2. So I'm going to multiply by 2. I get x equals negative pi. And then when I multiply by 2 on this one, I get x equals positive pi. Pretty easy with that one. We already have some nice asymptotes to draw in. And again, there's no need to do any scaling on this one. So we can just use the scaling that's already here. So I'm going to scroll down, draw this vertical asymptote at negative pi. Do this again over here at positive pi. So there are our vertical asymptotes, much wider this time. You may notice the reason for that. This factor of 1/2, that's really our b value. B equals 1/2. Whenever we have that fractional value there, we know it's going to stretch out horizontally. Our period is going to get elongated. When that number is bigger than 1, actually, it's going to scrunch in our period. It's going to shorten the period. So you may notice that from some previous things that we've done in this case. So now our period is from negative pi to positive pi. So that period here is actually 2 pi. So it's actually doubled our standard period of pi for tangent. Okay. Now we need to divide this cycle into 4 even increments. At this point, if there was no scaling here, we would want to make sure that it is provided. So here's the middle of our cycle at 0. And then here, over here, here's the 1/4 point, right? It's half of this half. And here's our 3/4 of the cycle. So now we split it up into these 4 even increments. 1, 2, 3, 4, and they're all nice and even. The next thing we need to do is think about our amplitude and midline. So in this problem, our amplitude is 4. And there is no reflection. This is kind of a standard tangent graph. It's not reflected at all. And our midline is actually down at -1 now. You could draw some guiding lines for these if you want. Some people really like these, so they put their midline down. And amplitude means I'm going to go above that and below that. So I need to go 4 above it, which would be here. And I need to go 4 below it, which is down here. Again, if you like these guiding lines, you can use them in the same way that you graphed like, secant, cosecant, sine, cosine if you want to. Again, it just helps line things up, but it's not necessary. And we're graphing tangent. So we need to graph those 3 points for a regular tangent graph. So in the middle of our period, it's in the middle on the midline. So that's right there, midline in the middle of our period on the midline. And then down here on the left side at the 1/4, we have to go down the amplitude. So here's our 1/4 point. We need to go down the amplitude from there, from the midline. So down 4 units from the midline. And then our 3/4 point, we need to go up the amplitude from the midline. So our 3/4 mark here, we need to go up 4 from there. There we go. Again, this one is kind of stretched out vertically like the last one. So it's not going to have quite as exaggerated of a curve, but it's mostly there. We want to try to sort of do our best with plotting this. Okay, let's go for it. All right. Here's our start of this. And I'm kind of running off. I don't really have enough to finish it on the other side. If I had more graph, I could show it approaching that asymptote. Anyway, we're just trying to do our best here. We're not necessarily looking for a perfect graph. If we want something that's really accurate, we'll just do it on Desmos. Anyway, we'll have that be the end of part 1 here, and we'll do some tangent graphs next, and I'll see you guys then.